Another radio-related topic, Fresnel oscillations, we know from radar. The Fresnel Transform is maybe less known, and also the subject exists already for a while, and now it's up to a revival. Joachim will tell us about it.
Thank you, Chris, for the introduction. So I'm a fourth-year PhD student at the Belgian Institute for Space Aeronomy, and this talk I'm presenting now is part of a research visit I did over the summer at Western University, Canada. So what we'll do today is to look at the fragmentation of small meteoroids using radar. For a bit of context, here's a video of a Gemini 2023 detected by high-resolution optical camera from the CAMO system. And if we look at the event start, we clearly see that at the beginning we have an homogeneous trail, and the meteor there is only one trail, while at the end, clearly the trail has broken up into two non-coaxial parts. And this phenomenon, of course, as you all know, is fragmentation. So why do we care about that? Well, fragmentation is important for a number of reasons. If we understand fragmentation, we can get better ablation behavior during the atmospheric entry. That allows us to better quantify the deceleration of the object in the atmosphere and hence get better dynamics in space, better orbits. But understanding fragmentation also allows us to get a better insight into the strength and the composition of object, and finally to get better density estimates, which are also very relevant for space agencies and satellite risk assessment. So here's an example of a meteoroid structure that has been brought back by the Rosetta mission, and we see that depending on the scale at which we look at the object, we see very different features. And basically, fragmentation is a way to infer the structure of the meteoroids. In particular, we want to look at small meteoroids because they are critical for satellites above the low Earth orbits and for interplanetary travel. And even more specifically, here we look at the threat regime, which is between 100 microns and 1 millimeter. And this is called the threat regime because this is the part of the meteoroid population which is sufficiently numerous to be so that we can quantify it statistically, and at the same time that can still do damage to spacecraft. And this threat regime can only be probed with radar setups, and this is why we want to look at that in the radar world. So far, in the state of the art, what have been done in terms of the study of fragmentation? Well, most of the work has been done through head echoes, so by the study of the dense ionized region, the dense ionized plasma in front of the meteoroid head. And in particular, the most convincing piece of evidence was obtained by Joachim with static measurements. So here I show some of the graphs that have been obtained. You see the power profiles that have been obtained at 3 different receivers for the same event. And what we see is that there is some interference pattern between in the amplitude curve, and this has been interpreted as being the velocity as being due to the interference beat between different fragments that move along the trail at different speeds. And so at some point they are in phase, at some other points they are out of phase, and because of that, well, you have these interference patterns which has been observed at different receivers at the same time. And when you compute the differential velocity, you obtain quite a good match between the receivers, which is a convincing proof for fragmentation. Now, what we are doing in this work is to look at the Fresnel Transform, which does not deal with head echoes, but with trail echoes. Basically, it's always good to remind, to use a little optical analogy. And to do so, I show here a graph which basically gives a light source, a given object, and that when the light source interferes with the object, we have a diffraction pattern. We know that very well in the optical world, but we have the same actually in the radio world. The only difference is that we don't have a diffraction pattern per se, but we simply observe radio amplitude fluctuations at our receivers. And so the Fresnel Transform is just that. It's using the amplitude fluctuations and trying to invert them to retrieve the source behavior, and this is the ionization curve. So most of you are familiar with the light curve in the optical domain, but in the radio world, we talk about ionization curve. So this is what we try to do, develop a Python package to characterize fragmentation with the Fresnel Transform. There has been some work done in the past for that. Here's an example from literature results. You see amplitude and phase of your radio signal. You compute the Fresnel Transform. I will skip the equations here. And you get some ionization curves. So what do we see here? If we look at the top graph, well, we see that we have some reflectivity function as a function of the position along the trail. So basically, in front of the meteoroid, of course, there is no plasma, no ionization, so we get pretty much zero. And then the moment you reach the meteoroid head, you have a sudden rise in your ionization, and progressively, as you go further away, as you move further up the trail, you get this exponential decay because the trail is diffusing, and so the ionization is being reduced. Now, what the authors say in the literature is that this exponential decay is not perfectly exponential, but there are some bumps here and there, which are basically the proof for fragmentation. And here we raise a question mark there because, well, to me, this is not super convincing that those little bumps here and there are actually fragments. Well, they could be due to a number of other factors. So here we want to verify that and go a bit further. So that's what I did during my stay, develop some software. Here I show example with simulated echoes. At the top, you see amplitude of your signal, phase of your signal, and the results of the Fresnel Transform at the bottom. And we see indeed that when we have a perfect simulated echo, well, we get this nice rise at the meteoroid head and progressively this exponential decay as we move further up the trail. Now, these curves already give a number of important scientific outputs. The exponential is, can give you the temperature of the atmosphere. The sharpness, you can optimize the sharpness of your curve, and that gives you an idea of your meteoroid speed. And if you look at the phase of the Fresnel Transform, we can get an idea of the wind drift. And so here already, the Fresnel Transform allows us to get a number of important scientific outputs. Now, in practice, nothing is perfect. We don't deal with simulated echoes, but we deal with actual echoes. And for that, we used the Canadian Meteor Orbit Radar. It's a 3-frequency radar. And what we see is that we have a sampling rate of 500 Hertz. That means that you get only 500 points a second. That is not a lot. And actually, if we look at simulated echoes with that lower PRF, so 500 points a second, for a velocity of 12 kilometers per second, so very slow meteoroid, everything works fine. We have those nice expected trail reflectivity curves. But when we look at a higher speed meteoroid, everything goes to garbage and, well, we cannot interpret anything. So that's the whole caveat that has been my nightmare for the whole summer, is that, well, whenever you get higher speed meteoroids, you are very limited by your sampling frequency. So this is something already to keep in mind. With simulations, we see that we need a high sampling rate to be able to perform that Fresnel Transform. Anyway, we wanted first to look at events and meteoroids which have been detected both in the radar and the optical world, so that we could compare maybe what we see optically with our eyes and what the radar tells us. And so this is an example of a meteoroid event that clearly shows a leading fragment here that is clearly appearing there. And here are the results of the Fresnel Transform obtained at the 3 CMOR frequencies, so 17, 29, and 38 megahertz. Let's have a zoom on that plot, which is the trail reflectivity, and let's see if we see any common features. This is not very obvious. At this point, what we would expect is that at least we would have some common bumps at common points, which would be the evidence for fragments. When you have the creation of a fragment, you expect that locally your trail, your reflectivity will increase, and so you would expect to have common bumps. But if you look at the peak of our blue curve, which is a 38 megahertz, and we look at if it corresponds to other bumps and other peaks, local peaks at the other frequencies, this is not very obvious. And so this is a bit concerning because it means that we already have a frequency bias. So with that in mind, we took a step back and we're like, okay, but since the beginning we say Fresnel Transform is ionization curve, and so it should match somehow the light curve that we see optically. So that's what we try to do. We try to compare our Fresnel Transform with the light curve of the optical record. So here is an event that has been detected both optically and also with the radar. And so we thought first, okay, let's try to superimpose and overlap our ionization curve given by the Fresnel transform with the light curve given by the optical record. The other idea we had was to say, well, instead of looking at the full light curve, we could just take one picture, one image of the high resolution camera and try to see if there is a match in the local trail brightness. So in that case, you don't take the full light curve, but you take one image and cross-section by cross-section, you extract the trail brightness. So this was two ideas we had. We tried to put everything together. You see the marked curves are the radar curves, and you see the light curves, which are given here, both for the narrow and the wide fields at the two CAMO stations. And well, if we make a zoom on that, it's again not very obvious. There is some matching for the radar curves, like up to 700 meters behind the meteoroid head, but they don't show any specific features that is comparable to the light curve. And if we look at the local brightness, so taking only one snapshot, well, there is not the same length scale. So the theory we have at the moment, but we need to go back to the drawing board, is to try to see if actually we are observing the same thing, because the radar is only looking at a portion of the trail. It's not looking at the full trail. The light curve extends for like 15, in that case, 20 kilometers maybe, while the radar only observes a portion of the trail. So maybe we are looking at the same phenomena, but from a different length scale. And so this is basically the whole conclusion, is that for now there is no certainty that the Fresnel transform gives us an actual ionization curve, but what we can say nonetheless is, so I'll conclude on that, sorry. The ionization behavior appears to be frequency dependent. We have frequency dominating effects, so that's a first thing. There is no clear match at the moment with the light curve. And the idea, the theory we have for that is that the Fresnel transform looks at a different length scale, so only 2 or 3 kilometers, and not like the full optical record as we do for the light curve. The caveat, the whole limitation, is that we are using a low PRF, which triggers aliasing for almost every echo. So now we are running tests at higher PRF, so about the factor 4 higher, to see if we'd get improvements in that. But in any case, even if the Fresnel transform does not give us fragmentation, does not allow us to look at ionization, it's still a very powerful tool for studying a number of things with trail echoes. We can get meteoroid speed, we can get atmospheric temperatures, and we can also get wind speed. So this is of relevance for a number of scientists. So I thank you for your attention.
Thank you, Joachim. That's making use the best possible of these combined techniques. Questions? Yes.
Yes, so CMOR has several remote receiver stations. So could you make a comparison between them to see if these matches?
Yeah, that's a very good point. That's what we had in mind. Like once we would have validated. So at 29 megahertz, indeed, we have like 6 remote stations. So the whole idea is to, at some point, to be able to follow the ionization along the trajectory, because they sample different points along the trajectory. So that's a goal we would like to reach at some point. Yeah.
More questions? More questions? Not really. Okay. Still a lot to do there. Thanks again, Joachim.